Good evening and welcome all present here. I am Anmol Bishnoi and today I'll be presenting the paper StyleGAN-T Unlocking the Power of GANs for Fast Large-Scale Text-to-Image Synthesis. The paper was published on 23rd Jan 2023 and it will also be one of the papers that will be presented at the International Conference for Machine Learning, which will be held in July this year. This is StyleGAN-T website, and I'll just play the video which shows images being generated using StyleGAN-T while discussing about the model. So StyleGAN-T has been making waves right now because it is basically a form of text to image synthesis, just like Stable Diffusion or DALI or models like that, except that instead of a diffusion model, it uses a GAN, that is a Generative Adversarial Network. A GAN in image generation is slightly old school when compared to the state-of-art diffusion models. Diffusion models work by removing noise iteratively. Uh, on iterations, they're removing more and more noise. Whereas GAN has two different types of two different models working together: the generative network and then the discriminator network. So what generator does is it takes in some sort of noise in a latent space. It takes a noise vector and then it generates images from that noise vector. Whereas you've got the discriminator, which tries to distinguish whether or not these images are real or whether they're generated from the generator network. GAN has the gradients, like in the GAN, the gradients from discriminator can go from the discriminator into the generator, and like thus making the generator better at generating more realistic images over time. So it is very interesting to see GANs again coming into the limelight, where diffusion models had stolen the entire scene of image generation. And yeah, so without further ado, let's jump right into the paper and we'll look into the abstract of the paper first. So text-to-image synthesis has recently seen significant progress thanks to large pre-trained language models, large-scale training data, and the introduction of scalable model families such as diffusion and autoregressive models. So here, I think we'd like to also pay attention to like why our why has image generation been becoming better and better. So a big uh, big credit goes to the large language models and large scale training data. So we've been able to instead of like changing the model architecture itself, what people have been doing is getting in more and more data and training the model for longer and longer durations of time, and just and increasing the parameters for the models, making the model go deeper and so on and so forth. So these diffusion models, however, require iterative evaluation to generate a single sample. So as I mentioned, diffusion models, they remove noise like uh, after like over multiple steps. In contrast, GANs only need a single forward process. So unlike diffusion models, GAN just require one forward pass, whereas in diffusion models you require like several forward passes to remove noise iteratively. And thus GANs are much faster, but they remain far behind the state of the art in large scale text to image synthesis. This paper, they are proposing the model StyleGAN-T, and yep, it addresses the specific requirements of large-scale text-to-image synthesis, such as large capacity, stable training on diverse datasets, strong text alignment, and controllable variation. StyleGAN-T significantly improves over previous GANs and outperforms distilled diffusion models the previous state of the art in fast text to image synthesis. So here what we'd like to note is fast text to image synthesis. Diffusion models have been doing a really good job in generating images, but using StyleGAN-T, we're trying to make it faster as well. So yeah, let's first training. Let's just jump right into this image. So here we're shown a graph with time to generate one image on the x-axis and zero shot FID 30K on the y-axis. So what is zero shot FID? FID is Frechet into inception distance. Frechet inception distance is used to assess the quality of images created by a generative model like a GAN or diffusion networks, which evaluates the distribution of generated images. FID compares the distribution of generated images with the distribution of a set of real images. So it will take a set of real images and it will take a set of generated images and find out it will just compare them. So the point to note here is lower the FID, the better. Now instead of rather than comparing images pixel by pixel, for example, the L2 norm, FID compares the mean and standard deviation of the deepest layer. So it just compares the mean and standard deviation of a batch of images. Right, so just like a L2 norm or the distance, lower FID means better. So here we can see that we've got stable diffusion. Stable diffusion has a very good FID, but it is taking about like 3 seconds. Then we've got ImageGen. ImageGen is a Google paper for generating images. They're doing even better than stable diffusion, but again, they're taking a lot of time. Whereas you've got StyleGAN-T here, they're claiming that you've got a decently good performance, not very bad, but the time to generate images is really good, really good. Less than half a second to generate a single image. So figure 1, quality versus speed in large scale text to image synthesis. StyleGAN-T greatly narrows the quality gap between GANs. So what they're showing here is GAN. So the previously, I think the best GAN that they're referring to here is Lafitte, and StyleGAN-T greatly narrows the gap between GANs and other modern families, and while like taking less time. So we've got really good FID scores now, and the benefit of GANs or generative networks is you just have one forward pass and you get very quick images, whereas these diffusion models will take time. And yeah, so that is pretty much what is written here in the introduction as well. So the primary benefits offered by GANs are inference speeds and control of synthesized result via latent space. Right, so GANs mein you've got the latent space, which is very beneficial when you want to make like incremental changes in pictures. So the images that you were seeing here previously, this is possible because you can get the latent space in GANs, right? And yeah, so they draw motivation from the observation that GANs had been lagging behind diffusion models. They had NVIDIA, so the authors with 1 were from University of Tübingen, and the authors with 2 had like correspondence, like had help from NVIDIA. So these were people from NVIDIA, and these 2 were from the University of Tübingen. Right. So they had really good systems, but for a limited time, and that was one of their constraints. All right. So just like we'll move on to StyleGAN-T. StyleGAN-T is shown to be based on StyleGAN-Excel. StyleGAN-Excel is again relatively recent, 2022. Similar to the original StyleGAN. So what StyleGAN-Excel did was StyleGAN-Excel has a unique discriminator design where multiple discriminator heads operate on feature projections from true frozen pre-trained feature extraction network. So you need to have text, right? And this text needs to be converted to some hidden latent representation so that you generate images. So they were using feature projections from two frozen pre-trained feature extraction networks. Their outputs are fed through randomized cross-channel and cross-scale mixing modules. This resulted in two feature pyramids with 4 resolution levels each that are then processed by 8 discriminator heads. So you'll see you'll see ahead that what that exactly means, what is happening in StyleGAN-T. The synthesis network for StyleGAN-XL is trained progressively, increasing the output resolution over time by introducing new synthesis layers. The discriminator structure does not change during training. Instead, the early low resolution images are upsampled as necessary to suit the discriminator. Yeah, so StyleGAN-T, right. So moving on to StyleGAN-T, they're using StyleGAN-XL as the baseline architecture. And in this section, they'll show modifications into StyleGAN-XL piece by piece, and then they'll show how these modifications helped in improving uh, the model. So they focused on the generator, the discriminator, and variation versus text alignment trade-off mechanisms. All right, so basically they're redesigning StyleGAN-XL to make StyleGAN-T, which will now have comparable results to the diffusion models. Uh, this is basically the video in frames, shown frame by frame. So a painting of a fox in the style of Starry Night, beautiful landscape of an ocean with mountain in the background and sun is setting. So these are two images generated by these following prompts. And if you can imagine the latent space being like 2 points, let's just say in a 2 or 3 dimensional space. So moving from this point to this point, you'll have several other points in between, and these were the images corresponding to the points between like these two main images. And similarly, between this image and the corgi's head, you've got points in between represented by these images, and so on. Right. So then you've got, yeah, this is just showing you how pictures, images being generated are points in latent space, and by uh, basically moving between those points you can generate other images. And yeah, so this might not be a straight line. So if you can imagine these points being in like a 2 dimensional or a 3 dimensional space, right? So now instead of this photo, the photo of a cute lion and the Tower of Babel being connected, like being a straight line, a straight walk across them, it can have like valleys and troughs. So basically you can have the um, the gradients being different at different points. So if you can see this image and this image, you can see probably the gradient corresponding to the background was much more greater than the gradient corresponding to the foreground. So what you can see here is a massive change in the background here and here and here and here, whereas the other parts are incrementally changing. So instead of viewing it as a straight line between them, so each image having like a successful equivalent amount of change, these can be like extreme in one direction while not changing at all in the other direction. So that is how you can imagine the latent space to be. Now, right, so let's read what they've got to say. Example images and interpolations. StyleGAN-T generates diverse samples matching the text prompt and allows for smooth interpolations between these prompts, illustrated as a single continuous interpolation in scanline order. Generating these 56 samples at 512 into 512 resolution takes 6 seconds on an NVIDIA RTX 3090. That is a consumer GPU. And 512 into 512 is a good resolution because most of the GANs that you'll see uh, were mostly playing around in like lower resolution images like MNIST and all. These were generated in still relatively high resolution, while a comparable grid takes up to several minutes with current diffusion models. So yeah, 6 seconds, really good time. The accompanying video further demonstrates the video that we just saw. Right, so now let's just move on to the model, StyleGAN-T, and how it works. Um, we've got A, B, C, D. We'll read through the uh, description and then understand what it means. So A, our generator architecture is closely related to StyleGAN-2, with the learned constant replaced with Fourier features and conditioning applied in a slightly different place. So as mentioned earlier, a GAN, a Generative Adversarial Network, has a generator, a discriminator, and generator tries to take some sort of noise vector, and using your text prompt it'll basically generate an image from the noise vector. So what you can see happening is, we've got a text prompt such as castle fauvism, and the text prompt goes into the clip text encoder. So what exactly is the clip encoder? Clip is contrastive language image pre-training. So this is basically a model which has been trained on a large body of text and images, right? And the benefit of Clip is that it's open source. So these days you'll see Clip being used in part in almost every large scale text to image generation model. So what Clip will can do is it can take in text and convert it into some hidden latent space, like some vector that models can understand what the text meant. And it can also take in images, so it can take in text and images, and it can convert those texts and images into the same latent space to see how close or how far um, a text prompt is to an image. So it can convert text and images to a latent space and basically us get help the model get some numerical value for some text, right? So what is happening is you give a text prompt, Clip converts it into a C context, and this context gets concatenated with into the Z space. The Z was the noise, and it comes out as W. And this W is then fed into every single layer of the generator network. The generator network, as you can see, what is happening is it has several different blocks: 8 into 8, 16 by 16, 32 by 32, 64 by 64, and so on. And what is happening is every block feeds into the next block, and it also gives the output which gets accumulated and finally given out as the generated image. So we'll read on. For each resolution, a generator block is executed and its contribution is accumulated to the image via dedicated 2 RGB layer. The generator blocks employ residual connections, a new second order style mechanism. So right, so as you saw here, right, we had 512 by 512 images being generating. So it is no coincidence that here also you've got a 512 by 512 block. So what is happening is, uh, the first block is generating an 8 by 8 image. This is giving you some information like how a more outward like representation what the image would have looked in 8 by 8, and then you get a 16 by 16 image, and based on like what resolution image you want, till that distance the blocks are gonna get executed and finally accumulated into an image via the 2 RGB channel. So we'll move on to B, right? So generator details. So each of these blocks is shown right here. The block first has upsample, so the previous block is giving you a 16 by 16 image, and if your current block is 32 by 32, you need to upsample it to 32 by 32, right? A 16 by 16 output. Then you've got mod conf. which is modulated convolution. This is something that they have basically created, they have come up with. And then you've got several of these residual layers, and after applying these residual layers you've got 2 RGB function, and the 2 RGB function is basically this output, which is being sent to the accumulator to generate the final image. And you've got one line going into the next block, so this will just repeat. So the first block will upsample, and like after these layers, it will have one part going to the accumulator and the next part going again to the next generator block, which will again upsample to 16 by 16 and so on. Now we'll look at the residual block. So what is happening in residual block? You again have two modulated convolution layers, and you've got from the first modulated convolution layer, one is going to the group norm, which is like batch norm, a standard type of normalization, and then you've got a residual going forward. And yeah, so every generator block not only gets information from the last block, it is also getting the context, the text prompt at every point. So this W goes in at every point. Now let's look at what modconv is. So modconv is their modulated convolution, which here takes in the W. So every generator block has to know that what exactly it is trying to generate. So it takes in W, does in an affine and a split function. So the split function is what they're calling the new second order style mechanism, which is a cross product and then a summation of the W context vector. And this goes in, does a cross product with the input, and then here you can see a convolution 3 by 3 layer. The convolutional layers have filters that basically go across your entire input space and give you an output. You've got a demod, then you've got these bias and noise steps, and finally you've got the leaky relu activation function. As you might already know, ReLU is rectified linear activation function, which basically gives y is equal to x when x is positive, but x equals to 0 when x is negative. Leaky ReLU is in the positive side it is the same, but in the negative side it still gives some very minuscule output. So instead of the line being a straight line at y is equal to 0 for x less than 0, you get a line with a very small slope. So for negative values of x, it still gives some value, right? And then we'll move on to the C discriminator architecture. So now our discriminator processes the intermediate tokens of a dyno trained vision transformer. So the thing to note here is our generator, it was using modulated convolutional layers to get output from the latent space. And the discriminator now, instead of using our modulated convolutional layers, it is now using vision transformers for discriminating, and it is using 5 identical discriminator heads. Text conditioning is done using projection at the end, right? So what you can see here, our generated image, it comes out of the generator, comes out and then goes into the dyno encoder. The dyno encoder first does augment and crop. So there are several different augmentation techniques. It is probably employing several of those together. It could be random cropping, affine layers, or maybe like increasing the brightness, contrast, several different methods. So this is just standard. And then the vision transformer basically tokenizes our image. So like a normal transformer tokenizes text, right? If you've got some text, it will make them into an embedded representation of tokens. Similarly, a vision-based transformer will divide the image into like segments, and these segments will then be encoded into a sequence of tokens, and then these sequence of tokens are being fed into discriminator layers. The discriminator layer is also getting the encoded representation of the text from the clip text encoder, so that it knows what exactly is it supposed to be to even classify it as being real or fake. And yeah, so you see, as you go deeper, you get um, our image goes through multiple layers of transformer, and these 5 identical discriminator heads get output from the dyno trained vision transformer. This As you go deeper, you get more and more abstract representation of the image. Like our first level, where it might contain information about, like, let's say eyes, lips. Now, as you go deeper, this information, you get like a more outward, more abstract information, like, let's say, head or person or human, right? So initially you'll have more specific information, and all of this then goes into the discriminator, which gives you output, right? So now, moving inside the discriminator head takes in a 1D sequence of tokens. It applies a 1D convolution. So while in images you might know of 2D convolution, which goes across like pixel by like across. So in a generated image, it goes across the x and y dimensions. If you've got only a 1D sequence of tokens, the 2D convolution doesn't really make sense. So we have a 1D convolution layer. Then you've got batch norm, leaky relu. Leaky relu then feeds into another convolution, another batch norm, more leaky relu. And then you also have one residual pathway from this leaky relu direct to this portion. And yeah, then it checks basically the this text, the encoded representation of and finds out a per token hinge loss. Per token hinge loss is basically a dot product of um, the tokens coming from here, from the encoded representation of the original text prompt, and the encoded representation that you're getting from the tokenized image as the transformer gives out. And you can basically understand this as more or less the distance in the embedded space between the original text prompt and the encoded representation. Right, so moving on, D, text prompt is embedded using clip and supplied to the generator and discriminator. We also employ a guidance term to further improve text alignment. So you see, these generated images, not only are they going to the discriminator, you're also sending them back to clip. So a random crop of the image upsampled and then being sent into clip image encoder. So as we know, clip can not only encode text into its embedded space, into its latent space, but it can also encode images into the latent space. And then you basically find out how much farther is the text encoding of the original prompt from the image encoding of the output of the generator. And this will be used as a guidance term to further improve text alignment. So that was basically what the an overview of the StyleGAN-T architecture. Moving on, so they're telling us about how they've redesigned the generator. You've got residual convolution. So as we aim to increase the model capacity, the generator must be able to scale. However, increase in generator's depth leads to an early mode collapse in training. So let's see what mode collapse is. So mode collapse is usually if you want your GAN to produce a wide variety of outputs. You want, for example, a different phase for every random input to your generator. However, if a generator produces an especially plausible output, the generator may learn to produce only that output. So what they're trying to say is, if you'll have multiple convolutional layers, right? We're using modulated convolution, but these are basically convolution, special version of convolution. You'll use multiple convolution layers, and the generator is going to learn something that the discriminator can't discriminate against. So you immediately reach a mode, like you reach very quickly an output that the discriminator isn't able to discriminate immediately, and guesses as being real. So every time you run it, the generator is going to generate the exact same image because it has already learned an image that the discriminator can't discriminate against. So now you'll not get much variety. And to get that variety, you're basically using residual convolution with a layer scale in between. So basically, every modular convolution layer will have a layer scale. So what they're doing is a layer scale of a low initial value of 10 to the power minus 5 allows gradually fading in the convolution layer's contribution. So basically decreasing the contribution of convolution layers so that the impact of every layer is not as much as um, the possible maximum, so that you don't immediately reach the mode, right? Moving forward, we're also, as a part of redesigning the generator, you've got stronger conditioning. The text to image setting is challenging because the factors of variation can vastly differ per prompt. Consider prompts a close-up of a face and a beautiful landscape. The first prompt should generate faces at varying eye color, skin color, and proportions, whereas the second should produce landscapes from different areas. In a style-based architecture, all of the variation has to be implemented by the per layer styles. Thus, the text conditioning may need to affect the styles much more strongly than was necessary for simpler settings. So, what what they're doing in StyleGAN-T is, instead of using ctext directly, so basically, in as a part of the generator, right? Instead of using the text directly, the text could have been a close-up of face or a beautiful landscape. And now the amount of variation, the directions of variation that should be possible in these two areas, in these two image prompts, vary significantly. So for face, while you might want to vary the expression, for the landscape, you might want to vary the background, the lighting, and whatnot, right? So a simple text prompt will not do it justice about the degree of variation that should be possible. So what they are doing is, instead of using the ctext directly, they're splitting it into three vectors of equal dimensions, and then getting a product of the getting a product and a sum. So what the crux of the operation is the element wise multiplication that effectively turns the affine transform into a second order polynomial network. So instead of now having the prompt in a 1D space, right? So you can either go forwards or backwards. Now you're basically doubling the dimensions in which you can vary gradients in, right? So this is what they were doing here. So W was concatenated uh, noise with the embedded representation of the original text prompt, and W goes in and you basically do some sort of split, and you're increasing the dimension of W from whatever the original dimension was to twice the original dimension, so that you get more room to change and more room to get different types of outputs. That was the redesigning of the generator that they showed. Now redesigning the discriminator. Redesigning the discriminator first had feature network. So for the feature network, they chose VITS trained with the self-supervised Dyn objective. So in the discriminator network, yeah, the first step, basically they used this, the Dino encoder. Right, one thing which we forgot to pay attention to was orange represents pre-trained layers, pre-trained boxes, pre-trained parts. Green is what we'll be training, and blue is just fixed functions. So like leaky relu and norm and upsample, random cropping. These are fixed functions. You aren't really doing much there. Like these are just mathematical functions. Then pre-trained are models that they've used which already existed, basically to improve performance and like not requiring to train a model from scratch. So here you can see they've used the clip encoders, image and text encoders. Then you've got the Dino encoder, which basically encodes images into the transformer's latent space, right? So one of their discriminator, uh, an attempt at redesigning the discriminator had the Dino transformer, the Dino uh, vision transformer being used. to convert the image into the latent space instead of using probably CNN networks, right? Then you've got the architecture. Our discriminator architecture is shown. The representation size and receptive field are same throughout the network. This isotropy allows to use the same architecture. Our discriminator heads are minimalistic as described. The residual convolutional kernel's width controls the head's receptive field in the token sequence. We found that 1D convolutions applied on the sequence perform just as well as 2D convolutions on spatially reshaped tokens. Batch norm is problematic. We use synchronous batch norm. Oh, right, yeah. So they're using batch norm here, right? But when you're trying to parallelize your job over several GPUs, batch norm is a cross GPU job because it requires communication between nodes of several GPUs. So now they use a variant that computes batch statistics on smaller virtual batches. So these batches exist within a GPU instead of across GPU bigger batch. And this batch statistics are not synchronized between devices but are calculated per local mini batch. Furthermore, we do not use running statistics and thus no additional communication overhead between GPUs introduced. And by having no additional communication overhead between GPUs, they're making the model further faster, which to begin with was the goal of their paper, basically getting a model, a GAN network, which is much faster than the diffusion networks, but also comes closer to performance in the diffusion networks as popular right now, like stable diffusion and so on. Finally, augmentation in the discriminator. We applied differentiable data augmentation with default parameters before the feature network in the discriminator. We use random crops as shown in figure 1, significantly improve FID and clip score. This considerable that a well-designed discriminator compared to StyleGAN Excel are simplified. Right, so what they're doing is just a random crop. So augmentation, this step, this data augmentation step, they've done something unique over here to that they found out was making their model performance much better, and that was a part of their discriminator architecture redesign. Then finally, you've got the variation versus text alignment trade-offs. So guiding the generator. StyleGAN Excel uses a pre-trained ImageNet classifier to provide additional gradients during training. And yeah, so what they are doing is they're using the clip image encoder instead of the ImageNet classifier that StyleGAN was using. And now what they're doing is they're calculating the L clip. L clip is a loss of a cause phase loss of the C image and C text. So this is what they're trying to say, is they're also adding clip guidance to it. So the generator being trained just on the basis of losses from the discriminator wasn't enough, and what they are now trying to also do is they're looking at loss from here, from this arm. So they're sending it back to the image encoder, and the clip guidance term is basically the loss L clip function, and a cause phase loss between C image, the embedded representation of the image from the generator, and the embedded representation of the text in the original prompt. And this additional loss guides the generation distribution towards images that are captioned similarly to the input text encoding according to clip. So basically this part guiding the generator using L clip, so they're using losses from two different places to guide our generator. Then finally guiding the text encoder. Interestingly, so yeah, so what this is, clip as shown here was frozen, right? Clip was a frozen network with pre-trained weights, and they're directly using it. But now what they did was they also guided the text encoder. So they then introduced a secondary phase where the generator is frozen and the text encoder becomes trainable instead. So now they're adding like more epochs or more iterations of training where they're freezing the generator and now training the clip instead, because clip itself is a model, right? And it is a deep model where weights can be, where errors can be propagated backwards and it can be better trained. So they found out that guiding the text encoder basically improved performance. Yep, and finally, you've got explicit truncation. Explicit truncation is typically variation has been traded to higher fidelity in GANs using truncation trick, where a sampled latent W is interpolated towards its mean with respect to the given conditioning input. Here, the given conditioning input is the embedded representation of the text prompt, and what the generator is doing is it is taking the text prompt and it is taking some random noise, right? And using the random noise and the text prompt, it is generating some image. Now, if you change the random noise to different values um, to several, like if you try the running the generator with different values of random noise, you'll find some mean for all of the different z's. So you change the z value without changing the c text, and then you'll find some generated mean image. So what the trick truncation does is it explicitly finds out the mean, so it knows where the mean is, then it'll use a random noise and generate a fresh new image, and then it'll performs so it'll interpolate between w prime and w. So what the model knows the w prime, which is basically the mean, and it knows w will be basically according to some random noise. So we implement truncation by tracking f during training and interpolating between w prime and w according to a scaling parameter, which is psi, at inference time. So now we'll try to understand it using this image. So 4 samples for the prompt, a graphite sketch of Eva Longoria with a different random Z was generated. Increasing the truncation, decreasing Xi, improves the text alignment according to mean clip score per row at the cost of lower variation. So here what we see is across columns are different values of Z, the random noise, and across rows is different values of Xi. So for a Xi of 1, here you can see 0 and 1. For 0, I'll get exactly W prime. And for 1, I'll get exactly W. If I'm at 0.5, then it will find the latent representation at exactly the midpoint between W prime and W and give me that as the output. So here you can see for um, different initial noise vectors, for 1, you're getting very different images, but as soon as you get it closer to 0, your images start looking the same. And yeah, so that is at the cost of lower variation, right? So you're increasing the clip score. The clip score is basically how close it is to how close the image embedded representation is to the original text representation, and you get closer and closer because it is closer to the mean value, right? So you get a higher clip score, but you get lower variation. So that is what they did. Truncation is used quite a lot in GANs, and they have also, right, so they're saying that truncation can further boost quality and alignment for a given sample, trading away some variation. So they're basically telling us another modification, another thing that they tried experimenting with to make their GAN perform better, get a higher clip score basically. So now we'll move on to quantitative comparison to state of the art. They've shown us a comparison with Stable Diffusion, EDIF, LDM, Glide. These are all diffusion models. Then we've got Lafitte, the last GAN, which was really good. And then you've got StyleGAN-T, which is the GAN that we are studying right now. Downsample to 64 by 64 pixels. So again, we're back to the toy data samples. What we have to see here is these diffusion models, they're giving good FID scores. So remember, FID scores, lower is better, but they're also taking a lot of time. So 26 seconds to generate an image, 10.9 to generate an image for glide, but StyleGAN is using 60 milliseconds, while Lafitte is taking 10 milliseconds. But Lafitte had much terrible FID score. StyleGAN-T improved that score by a large margin. Comparison of FID on MS Coco 256 by 256. So now we're back into slightly better, like usable images, actually images that you will probably use. And now StyleGAN-T is taking 0.1 of a second. It's got a score of 13.9, which when you see compare it to the state of the art that people have been using, Stable Diffusion 8.59, Imagen, this is from Google. They've got an even lower FID score. So what they're trying to bring to your attention is, even though it's got a lower score, it's taking 9.1 seconds for generating images, while we'll be able to generate images much faster, although not as close, but much faster. These results lead us to two conclusions. Firstly, GANs can match or even beat current DMs in large-scale text-to-image synthesis at low resolution. So yeah, we're able to beat them at low resolution. Here you can see 7.3 was better than any other, but low resolution isn't really useful for us because we're moving to higher and higher, like actually useful resolutions. So while FID slightly decreases in EDF1 when moving from 64 to 64 by 64 to 256 by 256, it currently almost doubles in StyleGAN-T. Right. So moving on, moving to higher definition images, our FID score almost doubles for StyleGAN-T. Therefore, it is evident that StyleGAN-T's super resolution stage is underperforming, causing a gap to the current state-of-the-art high resolution results. Whether this gap can be bridged simply with additional capacity or longer training is an open question. Right, a thing to remember, our authors didn't really have infinite training time with their GPUs. They had GPUs for a very short time. So yeah, that is what the gist of this entire paper ends up being, that for lower quality images, we are able to beat it. We are able to beat diffusion models at much higher speeds, but for higher quality images, we're able to do much better than before, much faster, but not really beat. We're not really close to beating any diffusion model yet. And comparing text alignment trade-offs, so FID clip scores of StyleGAN-T, distilled, stable diffusion, and EDF1. We report values of SD distilled. Right, so this is a zero shot FID on the y-axis, clip score on the x-axis. Clip score higher is better, zero shot FID lower is better. So for SD distilled, which is distilled stable diffusion, the guidance scale of W equal to 4, basically more passes. So SD distilled increases the number of sampling steps to 248. So at two passes, diffusion model, if you remember, it removes noise for more number of passes. So as you increase the number of passes, you're increasing your clip score and you're decreasing your zero shot FID. And if you'll know, like stable diffusion uses a lot more passes, so this graph will actually go further down here. But again, it's going to take a lot more time. So I think they're trying to keep it around the same time. So when models are taking around the same time, this is the comparison of model performance. So StyleGAN-T is here, EDF1 is here, and then when you're using stable diffusion with, albeit with lower number of sampling steps, you are here. Then you've got text encoder, right? So we were originally using the clip encoder. If we use the clip encoder as is, this is the graph that they observed. So clip score again higher is better, zero shot FID lower is better. So they were getting this sort of graph, but when they also trained their text encoder, so freezing the and the generator layers and training the text encoder, the clip instead, they were able to shift the FID clip score to the right. So basically get more clip score for the same FID. Using truncation, StyleGAN-T can push the clip score to 0.305, successfully improving text alignment. StyleGAN-T outperforms SD Distill in both FID and clip scores, yet remains behind EDIF1. Right, so that was just this explaining this graph. And yeah, a big part of using generators, the GAN networks, is the potential for easy latent manipulation. So you already have the latent, you can find out the latent representation of images, right? The original latent space that they were generated from, and now basically from one latent space to other latent space, uh, you can move in that direction and get different outputs. And once you've got one image, you know what direction to move in to basically get any changes. Then you can do it to any other image as well. So if you already have a Victorian house and you know what direction a modern house is in, you can take any Victorian house and move it in the direction of modern house. So that's one benefit of StyleGAN-T. It enables latent manipulation. Qualitative results, they basically want us to see these images. So as you can see, the real photo doesn't really look that good. All of the others, like for all of these text to image generators, you don't really want to pay much attention to the other things. Like the real photos, generating real photos is the actual hard part. uh, these artistic styles, anime, chalk art, still give you an opportunity of like a flexibility, and allows you to uh, the flexibility allows you to still make it feel realistic, like to a human they'll still look good, right? But a real photo is when you'll actually be able to see the differences and find out where what models are performing better. So as you can see, StyleGAN-T isn't really that good, while state-of-the-art models have started to be real good, even in generating real photos. This is probably a higher resolution image too, so as we could see, our diffusion models, they're much better than our StyleGAN-T. Finally, failure cases. StyleGAN-T can struggle to bind attributes to objects. A red cube on a blue cube. Yep, it completely forgot what a blue cube is supposed to be. Just made a red cube with a blue background. Astronaut child's drawing. Yep, it's tried. A sign that says deep learning. Yep, so these GAN networks especially are unable to understand at least written text, so they're not able to generate written text to that good extent. Limitations and future work. Similar to DALL-E that uses clip as underlying model, StyleGAN-T sometimes struggles in terms of binding attributes to objects as well as producing coherent text and images. So alright, so these are uh, more to do with how clip isn't able to bind text to images, attribute to images. The latent representation, the embedded space for clip isn't that good, and we're not able to generate that good of images. So maybe using a larger language model would likely resolve this issue. So if people come up with a better model than clip, we'll be able to do it better. Guidance via clip loss is vital for good text alignment, but high guidance strength results in image artifacts. Right, so in the generator network, we were propagating losses not only from the clip loss but also from the discriminator. So they're saying that if they're increasing the strength of the clip loss, we're getting image artifacts. A possible solution should be to retrain clip on a higher resolution data. So again, they're blaming it on clip, and improvements in clip will improve their model as well. Truncation improves text alignment but differs from guidance in diffusion models in two important ways. While truncation is always towards a single mode, guidance can at least theoretically be arbitrarily multimodal. Right, so truncation moves our image from noise towards the mean, but this is assuming that there's only one mean, and truncation can be theoretically multimodal. So there can be several different peaks, several different means, several different values that give the highest clip score. So um, alternative methods for truncation might further improve results. Improved super resolution stages. So we had 8 by 8 being converted to 16 by 16 to 32 by 32 and so on. So if they get higher capacity and longer training, of course it'll get better. So uh, I mentioned how an important point of why models are getting better these days is because these huge organizations, OpenAI, Microsoft, Google, have tons and tons of GPU. They're running their models for longer and longer durations of time using bigger and bigger data sets. And that is why our model, the stable diffusion model, in fact, is also much, much larger, has trained for much longer than StyleGAN. And if StyleGAN is able to get higher capacity, gets more nodes for longer times, then it might be better. It should be theoretically better. Then methods for personalizing diffusion models have become popular. They fine-tune a pre-trained model to associate a unique identifier with a given subject, allowing it to synthesize novel images of the same subject in novel contexts. Such approaches could be similarly applied to GANs. Right, so yep, that is it with StyleGAN-T. I hope you've understood this recent paper, this paper that had been making waves about a GAN that was again claiming to be good at generating images as good as diffusion. And yep, that's pretty much it. If you've got any doubts, you can hit me up. Thank you.